Thanks, John, and thanks, everybody. A few things before we get started. I do have a bag of parts, so we can look at that. You can just come look at it anytime, even in the middle of the talk. I don't particularly care. No, I don't want to pass them around. They go missing. And that's the problem. Especially this really cool looking blue one right here. It's the only one I have left because all the other ones have been stolen from me. So I'll watch that one like a hawk. Another thing, the interactiveness. Just feel free to ask questions anytime. Raise a hand, shout a question out. I particularly love that. I love discourse, agree or disagree. I'm actually really fond of that. So if you have any questions about any of the topics we talk about, that would be awesome. Third, I say this on the beginning of most of my talks. I can't promise it'll be good, but it'll be entertaining. So it's okay to laugh. This is not really intended to be super deep. This is not part of your curriculum, so you don't have to memorize anything. It should be fun. And then the last thing, a few things about me. I have 4 kids, ranging in ages from 9 down to almost 2. So I'm a family man. I love to roast coffee. I'm a little bit of a coffee snob, an aficionado for roast profiles all the way from bean to cup. So if you have an interest in that, I'd love to. Yeah, coffee is life. And then my other hobbies are basically my work, which I hope that you can kind of see some of the stuff that I'm passionate about, that I've worked on in my career. So this is a presentation, and we'll get started. So just a quick agenda. Who am I? Why should you care? The answer is probably you shouldn't, but I'll try to make you think that you should. We'll go ahead and talk about, med device, additive orthopedics, specifically with a focus on computational design, which is my specialty. Another quick segue, if you want to know about who I am or what I do, look up my name on LinkedIn. I'm a LinkedIn advocate. Somebody has called me a LinkedIn influencer, just because I post all the time, and this stuff is really, really super fun and important to me. So we're going to talk a little bit about bone and kind of the ecosystem with which bone loves to live. In the context of med device, we'll talk a little bit about reducing stiffness and why that matters, a history of additive and orthopedic devices, some limitations which lead to computational modeling, the fun stuff that I get to play with. Talk about a few case studies in biomimicry, which is one of my passions, and then go through a couple case studies, and then I believe that you guys have tinkered a little bit with NTOP, maybe some of you more than others, but I also have a few applications that I have on my computer and willing to kind of walk through some of that stuff live, or if anybody has any questions about it. Again, I have fun with it. So a little bit about me. I've been in orthopedic devices my entire career, about half of it on the design and development side, half of it on the additive manufacturing side. I've always been and will continue to be an advocate for advanced manufacturing in orthopedic devices. I actually just recently transitioned from a startup company that was additive manufacturing for orthopedic devices from about 2017 to 2023, and transitioned into a consultation role. I told John that I'm going to give it a year. I'm going to give it a year, kind of see how it goes. I think there's a lot of opportunity in the space right now for subject matter expertise as applied to orthopedic devices in general, especially with regards to advanced design. If anybody has used topology at all, you know that it can be kind of a bear to deal with. And between that as well as the regulatory side, there's a lot of opportunity, I think, to come alongside companies and really help them out with some of their workflows. A little about me. So I did a double major in mechanical engineering and biomedical engineering with a minor in math. I started out my career developing spinal implants. I worked for a little bit of a cowboy in the space. He founded a spine company. He was a former neurosurgeon. And one of his biggest things was kind of trying to look at various surgical techniques that were out there and invent new ones. He was a little bit of a narcissist in a good way. So we developed one of the very first interspinous clamps. That was a posterior fixation that goes on your interspinous processes, or the bumps on your back. One of the very first fully cannulated sacroiliac screws for hip mobility fixation. And then the first sterile package cervical plating system. Sterile packaging is something we may get into a little bit later as far as regulated medical devices and how that goes. I was a pretty early stage researcher for AM, specifically titanium and spine, starting in 2013. And we'll go a little bit through the history and about how orthopedic or additive has sort of entered orthopedic devices. Early adopter of computational design tools for ortho. Grasshopper, I believe, was released in 2007. I started using it basically alongside SolidWorks in 2006, my first year at college, as well as Anthropology Element. I'm a founder of Tangible Solutions, which is now Marl Tangible, contract manufacturer of 3D printed implants. So went from 4 dudes in a gigantic, dirty space with no machines whatsoever to almost 50 people in about 4 years. They were kind of recognized as having one of the largest portfolios of clear devices as a contract manufacturer. So I've got to touch a lot of stuff, a myriad of computational designs launched to market, and something you probably wouldn't know if you've been in medical devices for any length of time, but really, I don't know, in-depth conversations with the FDA about this particular stuff, like John mentioned, regulated devices. I love to speak on computational design and biomimicry. I am very passionate about it, especially my favorite animal, which we'll get into later. And then I founded Not a Robot Engineering, slight inside joke, this year to help customers take their designs to the next level. So let's talk about, is there anybody here that's taken any sort of like bio classes at all? Sort of. So like any ecosystem, any biological ecosystem, bone is similar. There is a natural stasis that essentially your body likes to be in. A lot of that's dependent on age, weight, other classifications, but typically there's a homeostasis that bone loves to be in, and then there's a dip on either side. One of those is disuse. You guys, I'm sure, have heard of osteoporosis. Disuse leads to bone resorption, essentially the body taking the calcium from the bone, and overuse is deposition, basically bone growth, which is of particular importance when we're talking about orthopedic devices and how we reduce stiffness. So Wolfsall basically says that bones will adapt to a degree of loading their surrounding environments. There's been a ton of studies that show that there's a certain amount of microstrain that the bones really love. And a decrease in stress on the bone will cause the bone layer to weaken. So if somebody has an accident and they need to get a plate to heal a fracture, it is of particular importance that the stiffness be in the right range. Otherwise, things start to go haywire. So that was back in the 19th century when Julius Wolff first came up with sort of these rules without, honestly, a lot of underlying science. In the 1960s, Harold Frost came up with what he called the mechanostat theorem, which is basically that there's a mechanism, a metabolic mechanism that monitors bone. It's a fairly complicated system, but he was trying to deal with it as a hierarchy, right? So he basically said the modeling, there's a certain range that adapts to overload conditions, and then there's the resorption. So basically having essentially an ideal microstrain, which we'll look at the chart next, is super important. And so recent literature, I think as of 2021, has reaffirmed the mechanostat theory and the importance of targeted microstrain, which again, in the engineering world, we deal with stresses and strains and displacements and things like that. So, here's a graph that is fairly prevalent in I would say spine, any bio engineering discipline. So there's actually a fairly small key zone that you have to play with, and this is microstrain. So it's minimum effective microstrain, and then you can see here that you've got this normal stasis, 200 to 2,000 microstrain. You've got this disuse condition, which is actually fairly common in most implantation scenarios when I've got a really stiff titanium cage going inside the body. And then there's the pathologic overload. That basically is like too much. It usually leads to improper bone formation. And then there's this key zone right where we want it to be, 2,000 to 4,000 microstrain. Of particular importance, we'll see later for anything to do with like computational design, because we can target those things very easily with computational design, where traditional CAD, we would have never had a shot. This is a fairly common study that has been done over the years, and one of those that they started to notice is when someone would get a hip replacement, especially when they first came out, it wasn't uncommon for you to go a few years before you needed a revision surgery. And that was, eventually they got to 5 years. I think my dad's had both of his hips done. I think they tell him 10 years probably before you're going to need some sort of revision. And so this has been something that's been well studied. And essentially the problem comes is, bone's used to a certain amount of movement. Over time, it develops its own formation, right? It solidifies due to the loading conditions. When you stick a gigantic, stem of titanium in it, the areas, you can see my cursor on. So the areas on the side here especially do not have the same amount of strain as they used to. And basically all of the load is now, this titanium implant. And so these particular areas over here, the bone weakens and loosens, and then over time, this thing, eventually will fail. So less than 1% of the ultimate strength of bone, changes in that small of a loading scenario can cause the bone remodeling to decrease after just a few months. So it's really important that this homeostasis be established pretty soon after surgery or there are issues. So low stiffness stems are something that's been in design, I'd say, for the last decade, 10, 15 years. And so they have had a profound effect on the stress shielding problem. So that's kind of the first foray into, all right, this is the original implant. This is what we've done. We've realized there's a problem with it, and what do we need to do to change it? And eventually people realize that, all right, well, while titanium is an excellent material for biocompatibility, the problem is it's just too stiff. You can see here cortical bone and cancellous bone are anywhere in the range of a couple gigapascals to 20. Titanium alloy, the Ti-64 or grade 23, is about 110. So far, far beyond what the bone stiffness is used to. But again, I think one of the very first spinal disc replacement surgery was literally just like a steel ball bearing that a surgeon just shoved in between two spinal segments. And that's kind of how it went from. Eventually, they standardized the shape. But typically, the picture that you see up here, this is one of the implants that I designed. It's a fairly square shape. These top and bottom pieces are called end plates, and the angle between the end plates may change depending on the curvature of the spine. But the problem is they were too stiff. And there was all sorts of adjacent level problems. That basically means somebody goes in, they get a back surgery, L4, L5. It's okay for a year or two, but then they start to have adjacent segment issues. So then they're right back into surgery because the disc right below it or above it has failed as well. So they're starting to see all of these adjacent level issues, which in spine, that's like Wolff's Law is really big, right? Well, you put a giant chunk of metal in there that's 40 times the stiffness of what it's supposed to be, and what do you expect? So people are like, well, duh, but what can we do about it? Like, at least the person's not dealing with nerve pain for the rest of their life. Go ahead. So titanium has probably a 70-year history of biocompatibility. And so I would say originally when the first stainless steels came out, because of their corrosion resistance, anything prior to that somebody would do with like a fixation plate that was like a steel that had more carbon in it would have corroded inside the body and caused all sorts of issues with infections and stuff. When stainlesses first came out, the lack of corrosion resistance was kind of a little bit of an epiphany because they could be placed in the body and there would be no adverse effects. The incision would actually close. A lot of times back in the day, you put a bone plate on and the incision would never close. The person would have like an open wound the rest of their life. And so titanium, I believe, was first investigated for aerospace usage. But by the time titanium came about, at least the alloys, the stainless steels had already been in use enough that people picked up on how biocompatibility was so important, as well as corrosion resistance. So, follow up. So that's a great question, and we're going to get into that. So the titanium is not just biocompatible, which is great, right? The bones or the tissue surrounding doesn't reject it, but it's also what we call osteoconductive, and this is something that is tied to probably PhD projects far above what I'm capable of understanding. But it's basically like surface energy, so it's osteoconductive, meaning for some reason it's attributed to characteristics, surface energy, other things like that, the surface roughness. Bone loves it. It'll grow onto it. Any crevice that's in the part itself, bone, like it's like a magnet to it. And typically, if you look at like fusion rates or the interdigitation of bone as it grows into implants, titanium has one of the highest osteoconductivities of any material that people have put in the body. The downside, again, is that it was too stiff. So in the early 2000s, the commercialization of PEEK, polyether ether ketone, made its way through a company called Envibio. So I think PEEK has been around since the 1980s as like a polymer. But again, somebody went through the trouble of doing the studies, found that it was biocompatible, and it also was way less stiff. And so they started to be able to, basically Envibio started licensing this material to spine companies to use in their surgeries because of their reduced stiffness. And so the stiffness reduction was great. It actually led to a drastically decreased subsidence, which is basically like you've got, two bones and then the cage in the middle, and you imagine something that's way more stiff than the two bones. If there's any additional loading on that, it just punches through the bottom of your vertebral body. It's called subsidence. That's typically a pretty bad thing, because then the disc collapses, you don't restore the height, and your nerves get pinched, and it was like you never put anything in. So this was like way better in that respect. The downside is, though it's biocompatible, it lacks osteogenic capabilities. So if there was a revision that was needed, the surgeons were going in to the same spot that they implanted something a year, 2, 3 years ago. And essentially what was happening was the bone never grew into it, or it didn't even like to touch it. It basically created this capsule of fibrous tissue that wasn't actually bone around the implant. So the surgeons could essentially go right into there and like pop them out, which was concerning, because it's like this thing is supposed to, there's a lot of movement, right? A lot of forces and stuff on this. So that's when they started spraying the tops and bottom of these with titanium. It's called a titanium plasma spray. The start of the plasma spray in titanium was about 2013, 2014, when I was first getting into this particular style of design. And a lot of the problems associated with it was terrible to sterilize. It dissociated, means it would peel off the top of the PEEK when you hammered it into the body. Has anybody ever seen like a orthopedic surgery, by the way? It's brutal. I mean, it's like carpentry. The guys that do the head, like I love dealing with neurosurgeons. They want the fine-handled instruments, right? They're brain surgeons. They typically are gentle. But if you've ever seen a hip or a knee surgery, like I don't know if this grosses you out, but you should just look up like something that's readily available. They're hacking, sawing. They have these things called a slap hammer, which are like this rod, and they have this weight on it. So basically, the weight allows them to get momentum, and it's brutal, especially revision surgery where they're trying to take something that's like that has solidified in the body out. So, but anyway, so there's a lot of forces on this stuff. So when these cages were getting impacted into the body, the top and bottom plasma spray layers were just like peeling off, which is, again, dissociation was bad. Anything that's left inside the body, even a particle, can cause an inflammation, can cause an infection. So these sort of fell out of favor. The other thing, you'll notice this hole on the top. Because PEEK is radiolucent, you can't see it on X-ray during a surgery. So surgeons were having a hard time positioning these in like a 3D plane inside the body using 2D X-rays. And so you had to drill and then place tantalum markers or titanium markers, which also became a problem because the fit mattered, the location mattered, it was expensive. Plasma spray is extraordinarily expensive. It's a not very controlled technology. So, what's the next step? And that's additive. So quick history, some of you guys may know this. Early 1980s, Chuck Hall is known as the inventor of stereolithography, which is the first 3D printing technology. The late 1980s saw the invention of SLS, so that's selective laser sintering, which has led to modern, what we call now powder bed fusion, which is, powder of, whatever your material choice is, and then a laser to melt each layer together in X, Y for as many Z layers as you want. 1999 was the earliest description of the use of 3D in spine surgery. Is actually a mentor of mine, Dr. Paul DeUrso, who's the founder of a company called Anatomics. Look them up. They're a super awesome company. They do patient-specific sort of templates and guides, as well as patient-specific implants, especially for humanitarian cases like intermedullary nails, as well as like maxillocraniofacial, like half hemispheres of entire sort of replaced craniectomies. In 2010 was actually one of the first FDA approvals for an AM implant, and that uses a technology called electron beam, which is slightly different than laser. Well, I would say, all the technologies melt powder, but electron beam is a little bit of a different energy type. 2010 to 2015, I like to call it the quiet era. So there was a ton of papers, you can see the ramp there, published in that time period, but the vast majority of them had nothing to do with implants. Everyone was looking at how they could use 3D printing for guides, medical modeling, screw placement, because screw placement, again, if I only have x-rays, right, a 2D x-ray, it's really hard to navigate a 3D target path, and you've got all sorts of this anatomy you want to hit, right? Spinal cord principle among them. And so in 2015, Stryker, which, if you read anything about Stryker, they're one of the pioneers of AM and orthopedic devices. They released their tritanium cages. At the same time, KTM, which actually Stryker ended up buying, released their Cascadia implants. And those are posterior lumbar cages. Honestly, one of the easiest cages to get to the market because of the test requirements. And then from 2015 on, again, that was only about 8 years ago, there's been an explosion in the space. I think med device, other than aerospace, as far as regulated industries, sort of leads the charge for adoption of AM in their ecosystem. And you can just kind of go down to the list. Stryker, Paragon 28, a large extremities company, mostly dealing with foot and ankle. I was a part of the Sentinel Spine launch. We produced all their cages. That was one of our very first customers when I was at Tangible. And then SI screws, which was a really cool sort of next level thing in AM, because most of the cages are all compression based. So if I've got like sheets of material melted together and I'm going to compress them essentially along the same axis, it's not particularly challenging mechanically. Yeah, I probably should have backed up a little bit. But so the vast majority of spine surgery is because of degenerative disc disease, typically in patients that are over 70. So you've got your spinal column, which for the vast majority of your life is great. I don't know if any of you guys are not old enough to have back problems. I shouldn't even ask that question. Maybe some of you that have been in sports do. I've had 2 knee surgeries, so I'm a hot mess. So the spine, because of all the loads and the movement, is actually like one of your very fastest joints that start to decompose. As nice as that sounds. And the problem is, at every single segment of your spinal column, there's a disc in the middle of each of the bones, and there are exiting nerves that go from your main spinal cord out to the various parts of your body. And it's actually a really tiny spot. I mean, it's a couple millimeter circle. And so any disc damage, any flattening of the disc immediately causes pressure on those nerves, which most of the time manifests as like neuropathy. You just get random pain, or you can't feel something. It's numbness, tingling. And so, the majority of patients, again, over 70, it's more of a quality of life thing that you are able to take that flattened disc and restore the height. And so the easiest way to do that is essentially throw a spacer in the middle. So I use cage, spacer, inner body implant. Those are kind of used interchangeably, but it's essentially some sort of mechanism for restoring that disc height back to anatomically where it should be. That's a good question. Any other follow-up questions on that? Do we need to go through anatomical terms? Additive? Yeah, so all of them were being done traditionally manufactured. So 5-axis CNC, some wired EM. I mean, this is a manufacturing course, right? So I'm sure that you're familiar with several different types of manufacturing methods. Yeah, so the screws and stuff would be made on, like a mill turn piece of equipment. I don't know if any of you know what a Swiss machine is. It's got like multiple different axes for tools and stuff. So that's traditionally, I think, back when med device started becoming more like advanced machining. Typically, there were just aerospace companies repurposed to make med device. But typically, like, back when I was doing more of the design and development, it wasn't uncommon to have tolerances on your print for interfacing pieces plus or minus thousandth of an inch, or plus or minus 25 microns, depending on if you guys are metric or inch. I don't know. I'm particularly fond of metric. I like how all the zeros line up like they're supposed to. So what you notice, I think, as time started to go on was, that people started to realize like what the technology could do for them. I keep some of these small words. That's another degenerative thing that I have is bad eyesight. This last one, this Redpoint Medical, is really cool. So people started to get into these patient-specific type cases, and for both the Carlsmed and the Redpoint, we were able to support these novel types of submissions through the FDA, which is an interesting landscape, which we can talk about a little bit later. So we'll talk about like the design limitations, which is the space I like to play in, which is software. So by 2014, the technology, being able to produce a thing, a widget, in additive manufacturing had outpaced what designers were capable of creating, specifically because of CAD tools. So if you look at Grasshopper, architecture students, people that were in design and architecture, were already starting to utilize Grasshopper, which was more of a computational design tool, to make really intricate geometry. One of the very first sort of mainstream Grasshopper things that ever came out, I think, was in maybe a couple years prior to 2014, was actually in a Victoria's Secret show. So there was a 3D printed dress back in like 2012. And the founder of Entopology, Brad Rothenberg, was actually the architect who designed that. And he used Grasshopper. But in traditional engineering land, right, the use of SolidWorks, BTC Creo, NX, CATIA, things like that, that was all just like, here's my multiple steps. I extrude this shape. I make this cut. There started to become things like sweeps. I can cut like a screw thread with a helix. But very rarely were you creating any sort of intricate lattice or anything like that. So some of the early softwares, Grasshopper, this first stable release was 2014. A handful of people had used it prior just for playing in the space, playing with surfaces and stuff like that. Within medical was one of the first. That was one of the first sort of lattice technologies, being able to create like a stochastic or a randomized lattice. And an Entopology element sort of brought a little bit more order to it, basically giving you a designer a whole list of cells that they could play with. That all had been previously researched. Most people at that point had started to research different cubic cells based off biology. But the downside was nobody had made them readily available for modeling, right? So any engineer could use them. And honestly, in professional disciplines, engineers, they're not designers, right? They're interested in, will my product fail or not? So not really anybody was like playing around with the space creatively. It was like, well, this works for me. I'm going to design it this way. And it was even the early stuff, basic latticing, limited tool sets. They were hindered by meshing. Have any of you ever dealt with like STLs as a mesh? Repairing STLs, dealing with really complicated hundreds of megabytes or gigabytes of STLs is not very fun, especially when I first started, in the early 2010s. In 2018, NTOP platform came out, which is my computational modeler of choice. I actually have used it ever since 2017. I was one of the first alpha users. And it introduced what's called implicit modeling based off of signed distance fields. So it's all essentially representation on math. So an STL, typically 150 megabytes big, whereas a file in NTOP was kilobytes, 15 kilobytes big. And that's just because it was all implicitly represented as an equation. So allowing for this era of computational design to enter the engineering mainstream, again, where most people were used to, well, that's just in designer land, architects are using it to design pretty things. That's not really supposed to be in engineering. Now we had a little bit more of an accessible toolkit to play with. So there's pre-2020, again, only a few years ago. The state of the market was a little bit of roughness on the screw, but that's largely traditionally modeled. This has got this within medical lattice, which I think is gross looking. Everything else, you could make this traditionally CNC milled. Same for this. Like, this was pretty common, I think, in the mid-2010s as people used SolidWorks to create, like, fence patterns. And that did reduce the stiffness, but again, pretty primitive to what we're used to seeing now. Some of the new innovations, 2 of the 3 on the bottom, I was fortunate enough to be able to design the workflow for. But these are using more of these computational designs, right? The one on the left is a C-spine product. It uses AAA periodic minimal sheet architecture, TPMS field. The one on the right is sort of a series of coils. Shut up, I want to talk to you. And then the one in the middle is like a new era of SI screw. I think that's actually S2AI. So it's like some like deformity cases. Have you seen like the rods going up people's back, or like complex deformity has got, typically, if I've got a really bad scoliosis patient, I need to correct that deformity. And occasionally it means that I got to bring the rods all the way down close to the pelvis and then put one of these longer screws into the iliac crest or into the sacrum. So these particular screws are basically have this ball and socket up here, so they can rotate in an angle, and the rest of them allows for, again, bone ingrowth into the parts. Typically, a spine implant is probably 30 by 40 millimeters, and very rarely any more than 20 millimeters tall. You know, I mean, you can kind of get a sense for the scale with one of these. So we're not talking about anything big at all, but you know, typically something like this. You know, and the height, again, the angle of the top to the bottom surfaces are all typically based on patient anatomy. Here's one of the, you know, when we talk about software limitations, there's also a bevy of regulatory limitations, and I'll let you kind of peruse through that. But you know, as with any regulated industry, you know, all the testing has become standardized over the years, so you know exactly like what test methods do you have to perform, what sort of values do you have to hit. Back when I was first getting into the industry, there wasn't really actually any standardized numbers. You had to just prove that you were as good as like the last guys that made it through the FDA. And so it was actually fairly common for you to be buddies with a distributor of medical products and be like, hey, can you send me Stryker's cage? I need to do some reverse engineering on it. So they'd accidentally ship it to your location. You'd have 24 hours before you had to ship it out to like reverse engineer it. And then your reverse engineered competitor model became the baseline test for your device design. In, I think, 2018, a handful of papers came out authored by the FDA called the PEC papers. And basically the FDA was like, we're tired of you guys stealing other people's devices and like testing them, because what they realized is when you reverse engineered it, it was never as close to the actual thing. And so they started to realize your predicate device testing that never matched their original, the company's original testing. And so they released sort of the standardized list of percentiles, basically giving you the 5th, the 25th, the 50th, the 75th, and the 95th percentile to try to hit, so you could show your device was strong enough for all the stuff that had been submitted. I'm choosing the bottom 25th percentile characteristics. So for a lumbar cage, it needs to be able to have a 2% compressive yield of 5,000 newtons, which is a lot of weight. I mean, that's a lot of weight. And then it needs to be able to last 5 million cycles for 2,000 newtons. And similarly, the subsidence, you can see here, this is, I mean, an absolute crazy stiffness. 45,000 newton meters is kind of what the 25th percentile device was, just way too stiff. And this is, again, in the FDA's regulations. This is kind of like a requirement that you have to hit. So why is that? And so here's the big thing. The equivalents are predicated on devices that were legally marketed prior to May 28, 1976. And that was because at some point the FDA had to like make a rule. What is considered strong enough? And they're like, well, we did a history review and we noticed that all these devices prior to 1976, like they were pretty good. You know, there was not a lot of issues with them. So like my problem with this is what I think. I'm just like, what? Because you know, we're talking about like what 40-year-old standards that are like, you know, necessitating medical device requirements. Now, that's always really, really, really bothered me. So essentially, you have to prove that your device that's manufactured in 2023 meets some arcane standards of 50 years ago. And the problem is everything's just way too stiff. You know, there's not even any questions that it's too stiff, based again upon these biological laws. Yep. right. Yep, right. So the standards down here at the bottom, F2001 and 2924, were these specifications that the FDA now is like a recognized consensus standard. They basically say if you qualify to the standard, we consider your manufacturing process to be good enough for our standards. The downside is the manufacturer needs to be able to prove, like you said, part to part, plate to plate, printer to printer, every single thing inside their shop has a minimal amount of variance. Otherwise, I could print it on machine one, they could do all the testing, and then I put it on machine number 5, and like the thing explodes inside somebody's body. So the FDA has a unspoken 5% rule. Honestly, they really need to release some guidance on it. But basically, they don't want any of your machine variants to be less than 5% of the original test values when that customer submitted. So imagine I've got 5 dozen customers, and I have to basically keep track of where all of them tested at. So it was honestly a dumb way of doing it. So then ASTM came out with a harmonized standard, which was IQ, OQ, PQ. And in manufacturing land, that's process qualification. So basically, they just want you to say, here's this process that we've done. We've got some statistically significant results showing that here's our bell curve, and here's where our tail ends are. And then you do process monitoring over time. So it's just basically, X number of samples every month or whatever your frequency is for testing. And that's honestly, like when we first supported submission in 2017, the FDA asked 3 questions, and they were dumb questions. And honestly, I think anybody could have cleared whatever they wanted to in additive because it was so new. And then there was like second year COVID, 2021, they were like, whoa, we've been letting some not very great stuff in. And so then they were like, the bar stops here. And they started asking for way more information. And now I think a couple years later, it's really settled out because now the FDA has a lot of experts in place that have done additive for long enough. So some material scientists and some guys that have reviewed enough submissions. So that's definitely been interesting, like from the inside, is seeing, like, again, a regulatory body, like their job is to protect patient safety. It's been interesting to see the evolution of the FDA and what kind of questions that they ask over time. But here's the big thing is, the stiffness is a problem. And we know it's a problem based upon historical data and a lot of tests that have been done. And so basically functional structures, when we talk about why additive manufacturing and the stuff that I do is even useful, it's because we can balance strength and flexibility. High stiffness is correlated with subsidence and failure of fusion. But insufficient strength is going to cause a device to break inside the body. So again, there's brackets. So when you look at the left versus the right, strength and stiffness typically is linear. But when you've got the ability to do computationally design the materials, it actually doesn't have to be. And you can essentially have a threshold which maintains strength for your particular application by what I like to call moving material around. And we'll get into that a little bit later. I'll speed up a little bit. So old versus new. Old, the 50th percentile compressive force on a lumbar cage, 21,000 newtons. But look at the clinically relevant lumbar load, 500 newtons. So we're talking about a 40 times difference between what's clinically relevant for the body in that particular load and what the FDA requires as a baseline for like a 50th percentile device. And so this became, in my opinion, enough of a problem that the FDA is starting to reconsider some of these thresholds, simply because it's not good enough. You can get all the fusion that you want inside of a cage, but the biggest thing that we want to be able to say is like, look, everybody is different. There's a distribution of people, and we're requiring essentially a single standard for every single device in that particular product code. So here's like what I think is the exciting thing about what we can do with this computational modeling is it basically allows us to manipulate structures like in an unprecedented way. Like we've never really been able to take and I would say program every voxel of a material like we can now. And with additive manufacturing, you could print exactly what's on the screen. That's one of the big cells of tangible. We had an incredibly good process. And so, even defects, like a defect in material, a hole, a little bit of a crack, like printed like that. And so again, like every single portion, if you're an engineer, you want what is on your screen to look like that when you print it. And what it also does is allows us to deal with these monstrous data sets. I mean, everyone's heard of the prevalence of ChatGPT, but prior to ChatGPT, what have we used? Like engineers use statistics and like heuristics to be able to process data. And that computational modeling allows us to process these data sets and essentially translate them into engineering requirements. So, we've got this on the left here, we've got the standard gyroid, right? This computationally designed TPMS material, which can be represented as an equation. And you can see here all the ways that we can manipulate this particular structure in space. By grading the thickness, we can manipulate the cell size, we can grade it with a shape, we can map it helically, we can map it to like a periodic surface, and all of these things we're going to be able to do and manipulate for what sort of our end goals for testing are. And what I think is cool is if you look at inside the body, no bones that undergo any kind of loading are just like static necessarily. Over time, they essentially adapt to their loading conditions. And so when I'm designing a structure at all, I'm not just particularly looking at a static structure. I'm looking at the load cases in particular, and I can essentially, create any sort of computational sort of landscape that I want, and then essentially plug and play material types or structure and get sort of different things out of it. You can see here. Right. Yeah, it's actually a lot. It's actually a lot. We always would joke when we were talking about like the size ranges. It's the difference between like a really tiny, Asian lady and a gigantic Swedish dude. Like, I mean, you're talking about many times different, and a lot of that also depends on like bone quality. So most bones, you've got like the exterior bone is cortical bone. It's like harder. The fibers are oriented essentially parallel with the outside of the bone. And then you've got this trabecular bone in the middle, which is what a lot of people are trying to model when they model these bone or these structures, is they're modeling trabecular bone. It's basically the body's natural light weighting system for being able to maintain whatever the loading condition is, but not, be too heavy. And this is one of the reasons why computational designers study like aviary bones or avian bones a lot, is because they've got some really crazy biological mechanisms for drastically reducing weight while maintaining load. I'm working with a company right now that does CT scanning, and we're working on like modeling the bones of a toucan. And like the toucan, the beak is a bone, but it basically naturally like morphs into its skull, and you can see like the load pathways from essentially like its bite into its skull. It's super cool, but like how lightweight everything is really crazy. So that's been honestly a really great learning opportunity, is just to be able to this biomimicry stuff is really super cool. No, so most time all this stuff is not made its way. Patient specific is still pretty new. The vast majority of stuff for the last 50 years is what's called a standard kit. So basically, you've got 120 to 150 parts that you've got to put inside of a kit that goes to a surgery, and that's because you have to hit all these different sizes and shapes for whoever comes in and lays on the table. And patient specific, basically the promise is, well, I can go ahead and get a scan of this person, and bone density scan can be done through a few different types of scanning and then composited basically with like CT scan slices. And then you essentially run it through an algorithm like DICOM data, point clouds, or something like that to establish density. But that's some of the newer workflows that are still not yet released yet, is essentially being able to take that and say, I want a cage that not only locally conforms to the anatomy, but also is exactly what the patient needs. And that's, in my opinion, probably 3 to 7 years off still from the FDA recognizing it as a class 2, like a generally marketable device without a ton of extra studies and research that has to be done. But when we talk about like tuning stuff, because the whole thing about computational design is what kind of structures can I come up with? What can I tune? The one on the left, the stochastic lattice, basically uses what's called a Voronoi algorithm, which is an algorithm that subdivides space generally equally. And so usually you get these like polygons, these 3D polygons in space centered around points, whatever your spacing is. The stochastic lattice, the Voronoi algorithm, has existed for 30 plus years. And so this is a fairly common, like, if I'm going to do a test on a material, I'm going to compare it back to like a readily available, well-researched thing. And the two on the right are novel material types that I came up with over the last several years. And they're basically perforated, triply periodic minimal surface. And then the one on the right is remap. So basically, computationally, it's compressed in a single direction so that the volume fraction remains the same, but it's more springy. And so you can see here, with the exact same volume fraction, the same amount of material in the space, we're able to reduce the stiffness by up to 50% from the original cage, while maintaining average stress under the fatigue limit of titanium, which is particularly what I'm interested in, because I need this thing to last inside the body for the rest of its life. But by further functionally grading, then we can basically take that already good remapped perforated TPMS, and we can functionally grade it to the von Mises stress. So people are like, I use von Mises stress to identify critical failure points, right? Where my part's going to fail, how potentially it's going to fail. So we can then take that data as a point cloud, turn it into a field mathematically, and then use that to thicken the areas that see more stress and take material away from the areas that see no stress. So it's basically, you're bracketing away all the material that you don't need. And so you can see this here, the addition of material in a compressive scenario. We've got high stress, we add it, and we reduce it in low stress areas. So it's almost like, if you're trying to segment out data, you clip it. So it's like, I don't particularly care about this data over here, and I don't particularly care about this data over here. So we can basically use these computational tools to clip away all the material that we don't need and redistribute it. That's why I call it moving material. Redistribute it to areas that it's actually supposed to be in. And this is a technique that couldn't possibly have existed a handful of years ago. But yep, sure. Yeah, that typically would converge on a particular solution, whatever. But I'm sure, have you guys done like topology optimization? Some of you are familiar with that. Topology optimization as an algorithm essentially moves material to where it needs to be, and then you've got a volume fraction target, right? I want a 30% volume, but this still needs to be able to satisfy my load case. This is actually a little bit of a reverse problem. I don't want the device to be stiff. Very rarely do I want it to be stiff. So I need the material to be distributed in such a way that it's not stiff. And there's not a lot of commercially available algorithms that do that right now in a way that makes me happy in particular, which is why the vast majority of these things are all custom at this point. Until somebody comes, like Topology, I believe this week just released a new version of their software, and they have what's called field optimization, which I've used for the last year in beta. And it's an attempt to do that. It's basically removes the material that absolutely is useless, right? That's got a zero stress or strain condition, and then redistributes the rest of the material where it needs to be in a way that's both lattice and topology optimization. It's honestly super cool. Let's talk about my favorite thing. No, no. Short answer, no. Um, I mean, powder bed fusions, unless you're Velo, and they make some claims that I don't know it can be substantiated, but typically they follow the same principles as like FDM or like filament deposition. So if I've got something that starts out of nowhere in space, and my nozzle just starts printing something, and there's nothing underneath it, typically it's going to fail. Similarly, there's a certain angle because of the step over, which will probably fail because it's too close to horizontal. So I've got some sort of support material I've got to put underneath it. The other thing that's a problem with powder bed fusion is laser versus EBM is there's a lot of heat and there's a lot of residual stresses. So if I've got a loose bed of powder and I try to melt something that doesn't have any connection underneath it, then it's a pretty violent process. It's a laser, it's loose particles. If you watch it in slow motion, they kind of fly everywhere. There's usually gas flow that carries the soot away. So typically, if I try to melt something that's got nothing underneath it, that's also a bad thing. Horizontal surfaces with no support typically sag pretty bad, and before you get to a consolidated state, there's a ton of porosity in the material, which typically leads to dynamic failures. So, anytime you want to create some sort of spongy material, let's say, typically the path from A to B has to be as long as possible, right, like a spring. And usually that means there's some sort of overhanging angle that violates some rule. We can usually get away with it if our struts are small enough, but if you've got any sort of thermal mass, then typically you have a problem with it. Did that answer it, or? Yeah, so yeah, so Velo 3D has started to do that. I think they were one of the first that basically looked at pre-processing a model with all of the right energy density equations so that they could start those sorts of melts from scratch, typically from like a really tiny point. And there are other manufacturers that have started now looking at that. The problem is, and without getting too much into the weeds on it, the FDA is not particularly happy about what they consider more of a black box. In other words, the machine's ability to take every single SKU and slightly alter the beam path, the laser speed, the power to suit that particular condition. Because the FDA really only wants to test like one thing, your worst case, and you define your worst case through engineering principles. Like, this is the absolute worst case that the device design, and this is what I'm going to test. But then the FDA, it's like, well, if the machine can do all sorts of stuff, then you've got to set up some sort of design of experiments to prove that no one random SKU in the middle isn't like the worst case because of your parameters. So it's an interesting question, and that's, we talked to Velo years and years ago about their machines for use in medical, and that's one of the reasons why there's no Velo produced parts right now that are in orthopedic. There's no Velo produced implants because of that particular problem. They actually released a standard set of parameters which doesn't do any modulation to get around that because of the issues they were having. This is my favorite animal. If you can learn nothing else from this presentation, look up the peacock mantis shrimp. It's literally the coolest animal like on the planet. So basically, the mantis shrimp has clubs, these dactyl clubs, and it's got the fastest biological mechanism that's ever been studied in nature. So it basically, will go up to a crab or any random crustacean and use this club to, break its shell, break its armor. And these can go through thousands and thousands of repeated strikes with no degradation of their armor. So when I first was introduced to this little guy, it was actually a web comic by the Oatmeal. And I've seen I love the Oatmeal. I mean, back in college, like, it was my favorite web comic. So this came out, so I started to become obsessed with it. And then there was an article that came out, and one of the things that was mentioned in the article was how difficult it was to model this thing, even for the illustration that they put on the website. And so I was like, man, I wonder if this thing could be modeled computationally so that it would be readily accessible, to be able to use in a product, for impact resistance, armor, football helmets, things like that. And so I did it. Basically, what's interesting about this is it's this disconnected fibrous network, and it's not only helically mapped like a spring to elongate the distance from a compression standpoint, but it's also got sinusoidal waves in it as well. And what's really crazy about this, because of that disconnected construct, is if you just look at displacement values right in an analysis, this versus any other sort of cell type that you can put in like a cube when you do testing, increases displacement values without yield up to 40 times, which was really cool as somebody in the med device space trying to design stuff that's supposed to be flexible but still doesn't yield. And so this has not made its way into a human use product yet. This was mostly a research project, but it basically showed the power of being able to create this as a field inside of a software platform, and then being able to drag and drop inside of a product. Armor, helmet. Basically, you give it the space, and it can generate the structure inside of it. Another really cool example. I mean, you really wonder how like sheep can just smash heads with each other and not like get concussions. And so when you start looking at like what biology has that again has been naturally developed, like what I started to think is, why am I wasting the time modeling all these things from scratch when like I've got this entire canvas of biology to look at? And so like when we look at this again as computational modeling, we can basically say I've got a user selected force, or this may be like a vector field, right? Incoming forces. And we've got this sort of reverberation field. It's a series of surface fields that are created based upon the initial contact and force. And then we can create a few different cases. One, basically we redirect or transmit the loading force through. And the other, we basically can tune the material to absorb that particular loading, which is probably, again, for impact forces, you want to increase the amount of time that the force is active, which is why helmets and stuff have cushions and stuff in them. So this is, again, a really awesome use of computational design in the space. One of the newer ones that I've been working on is looking at the Mako Shark's scales. So not only are the scales incredibly cool, but basically it can angle or bristle these scales up to 50 degrees from horizontal. So in fluid dynamics, one of the problems is that there's drag on the skin. And so basically this creates sort of these turbulent forces, which you think, well, turbulence typically would be a bad thing versus like a laminar flow, but it actually decreases the drag on the water. And this was something, again, I didn't see any sort of readily available way to like potentially put this on a product or like a surface. So you said about creating the identical, and this shows you a little bit about the NTOP workflow, convert it to implicit geometry, the math form. So the mess in the middle is essentially locating it in such a way that it allows to be modeled. And any of you that, I don't know if you take, how many math classes you take, but one of the things that we utilize in computational design is called modulo. Basically, it's like your remainder, and it tells basically how to repeat a sequence in math in X, Y, and Z. And so once we kind of get it where we need it to be, we essentially repeat it repetitively through space. And once it sits as a field inside of topology, now it's usable. It can be applicable to any particular part that we want. So we can essentially apply the field to a shape. I had one sample of this, but it is out getting CT scanned right now, so I wasn't able to show it. But it's still really cool how you can, utilize the computational design commands to bring to life a lot of these sort of biological things, which is why, I love the biomimicry stuff. It's one of my favorites. There's a couple case studies. Does anybody have any questions that, before I can like blow through these pretty quickly. Yeah, I mean, it's no secret that STLs and basically any triangle representation of complicated materials are not very nice. So I'm a part of the 3MF consortium as an advisor. 3MF is a new file format, and they are looking at essentially implicit or volumetric representation. One of the things Entopology is looking at is what they call implicit interoperability. So they're interested in going straight from implicit to the machine. And usually that's done by creating slices right away. I think that the technical term for some of that is called like VDB. Basically, it's a way to translate data volumetrically to like an FEA solver so that you don't have to create a FE solid mesh to go back and forth. In the interim, I found one of the best ways is to mesh down to what gets your features there, at least in NTOP, and then use a simplify command. The algorithms have gotten a lot better recently, which essentially allows you to reduce your mesh, I would say about 50%. It's honestly, there's not a super good way to do it, especially if you're looking at extraordinarily small features of size and something fairly big. I was talking to we were talking earlier about Matt Perlman and the print foam, and he wants eventually to take like his like modeled technology and print like shipping containers with it. So he's trying to figure out, can he take an extraordinarily complicated sort of foam material that would be computationally designed and then like fill a shipping container with it. And the fact is, no, there's not really a good process right now to get all that data to a printer. Again, without bypassing mesh files entirely, which is what most people are trying to work on. So. So I've always been a what is it, left-brained engineer. I wasn't particularly great at the math and sciences. I'll be honest with you. I think it was an average. I was a C student, so I wasn't a very good college student. But I think that the biggest thing is you got to understand like your tool set in particular. So I'm a familiar NTOP like power user, and so the thing I always look at is, does there exist a math function that already gives me a good basis? So for the sheep horns, I was like, this actually looks like a triply periodic minimal surface field. It's got a little bit of elongation about the transverse, which we can do mathematically. So I like to start usually from a basis. I think this was like a gyroid field. And then the vast majority of stuff that comes after that is, does the unit cell that you create need to be patterned? And if so, you can use math functions, sines and cosines, to regularly tile the pattern in space. A lot of the fundamentals really are in math form, which is why I think it's unfortunate that a lot of especially mechanical engineering students don't necessarily get some of the math or programming side of things. And then similarly, the ability to at least be, we were talking about this earlier, my father's a computer science professor. I'm terrible at programming, and I wish that I would have learned more. And I think these sorts of skill sets and tools will only become, I think, more useful for those people that are in the design disciplines. Because anybody that's used Grasshopper or topology, it's just a different mathematical way to think. So not a super good amount of advice. I think it just takes time to be in a software and play around with some of the things. And I've got topology up. So if I'm looking at any field in topology, then this is a 2D slice of the field. Basically, where it transitions from colors is the isosurface, where the surface is going to be represented in space. And this is the way that I look at all of my workflows before I ever see a 3D part on the screen. In fact, 90% of the time, I never see a 3D part when I'm designing an topology. It's all fields. So if I've got a gyroid field, and I go ahead and look at the gyroid field, this is what it looks like. And again, where it passes from the purple to the teal is a surface in space. And I can query that by looking at by basically looking at the field and saying I want to give it a bounding box. That way I can investigate it, and then it'll show me what the surface looks like in space. But the being comfortable either in this form or in a math form, right? Same thing with programming. Programmers don't ever see any kind of GUI or the output. They need to be able to debug or code, just again looking at the lines of text that they have. So similarly, this and in Grasshopper that's got a series of nodes connected, a lot of the times, unless you query the output and are looking at it, you aren't going to know what it looks like. So it can be very disconcerting, especially for mechanical engineering students. I want something I can see and crush and model this cube and put this hole in it. But it's a little bit of a different, I think, principle than a lot of people are used to wrapping their brain around. This is why I said this has not really made its way into the engineering discipline until the last 5 years or so, because most engineers like the physical. They like to model in the physical. They're not used to these computational tool sets where they don't get to see something. So I think that's been a little bit of a problem that is useful to mention, as far as how could you, if you wanted to get into something like this, what are the things that you should learn? I've been a pretty big advocate as an alpha user for them to introduce traditional CAD tools in NTOP, but they've not. So to be honest with you, you shouldn't use it. it's way easier to use the SolidWorks or something like that to do most of your traditional design, and then use surfaces or something to segment out the thing that you want lattice. In my opinion, it's a little bit unfortunate in that you've got to use traditional CAD to kind of chop up your space and bring it into topology. But one of the nice things about end topology is, like, most of these cages are a pretty basic set of shapes, and so because NTOP's good at building workflows, you can actually design a whole cage inside of NTOP and then basically let the designer choose the width, the height, or whatever your variables are, and it'll auto-generate, which is one of the more powerful things about computational design software is I can bring in any blob, any design space, and its predetermined list of rules is going to give me the output that I want. One of the powerful things. I don't necessarily have to go in this too deep, but this is one of the applications that we did to show essentially flexibility without material yield. And the idea was essentially that we're getting far more displacement than what anybody would ever get, right, from a fusion standpoint through geometry manipulation. And so we were looking at 5 times the anatomical axial load, again for safety factor, and then a flexion extension because of body movement, while staying inside the fatigue limit. We designed the first pass. It was well over fatigue limit at 0.5 Newton meter. Really high strains, 1100 MPa max stress, which is about 300, megapascals over the yield strength of titanium. So this is kind of the NTOP workflow. So what we did was we used our principal stresses. We looked at that particular loading condition inside of topology, and this field is essentially like from 0 principal stress to max principal stress. It gives us a range inside of a mathematical way that we can look at these strains in 3D space. And we interpolated from the infimum to supremum, right, the smallest to the largest, and it's adjustable to the target output. So we basically said at 0% strain, we want to remove 50 microns of material, and at 0.4% strain, we wanted to add 132 microns of material from left to right. And what that led to was the secondary design, which has got drastically reduced principal strains, and no material had yielded over the fatigue limit of 420 MPa for titanium. That reduced our sort of max displacement some, but we weren't particularly clear about that. We were trying to design it within the limits that we had, and we wanted to, again, stay within the fatigue limit. So we look at our design goals. We were able to, I think I had put up here, maybe I didn't, I might have deleted that, but we essentially were able to drastically affect the performance of the device, and the difference from what we started with and what we ended with was only about 3% of material. So 3% of material was capable of transitioning the design from an easy failure, well over yield, to, again, moving the material in the spots that it was supposed to be to withstand that loading condition.